Hello, ladies and gentlemen, and welcome back. We're still looking at our 2018 Cimc paper. We are on to question number 6 in Part A. So this is the last of the final answer questions. It's the last of the questions that are worth 5 marks. The next 3 questions, the last 3 questions after this one, are our B part, where we will need to give written solutions. So let's just enjoy the fact that we can just hunt for our final answer one last time in question 6 here. So, what have we got for question 6? There are 20 chairs arranged in a circle. There are n people sitting in n different chairs. Okay. These n people stand, and they seem to each move k chairs clockwise. After this happens, exactly the same set of chairs is occupied. For example, if the... Oh, they're giving me some chairs. I want to just be able to visualize this, so I'll just scribble it off in the margin. I don't really have the space. I guess... What is it? 2, 4, 7, 9, 12... 4, I'm not going to remember that. Let's write a picture. I want a better circle to start with. There we go. 1, 2... Opposite 1 should be 11, 12. I just want to get nice, even spacing. Oops. 3, 4, 5, 6, 7, 8, 9, 10, 20, 19, 13, 14, 15, 16, 17, 18. Alright, that's pretty good. So what did they say? 2, 4, I think there was a 7 in there. 2, 4, 7, 9, 12, 14. And what was the last one? Oh, 17 and 19. Oh, look at that. These guys are opposite each other. That's kind of an interesting observation. But, okay, so everybody moves... What's their example? 8 chairs are occupied, and then everybody moves 15 chairs clockwise. So 2 will go all the way to 17. So going 15 around is sort of like going 5 backwards. 4 will go to 19. 9 would go to 20 with 11 moves, and then 1, 2, 3, 4 makes 15 moves. So it does work, but the 2 sort of has nothing to do with the 4. So we sort of get... Well, we can use some color here. We get one group of 4 that sort of move amongst themselves when you shift by 15, and then we get the red group with 2 and 7 and so on that shift in the same way, but they shift amongst themselves. All right. So I understand their example here. So 8 chairs, those 8 chairs, and 15 clockwise. Now what do we want to know? For how many pairs nk, with n between 1 and 20 and k between 1 and 20, is this possible? So we don't actually care about the specific configuration of 2nd, 4th, 7th. That doesn't seem to matter. So all they want to know is, all they're saying is, if n is 8 and k is 15, there's a way to do it. So, okay, so what can we do here? Well, I think probably the first thing is to take a look at why this is working, and I would say it's because, well, you've broken the number of people down into sort of these little squares. Are there other shapes that could work? So it's 8 people, but it's sort of 2 groups of 4. So could I do 12? If everyone shifts 15? Well, sure, start with 3. We'll add 3 to the mix. And then 3, if you move 15 over, will go to 18. And 18 would go to 13, because moving 15 clockwise is the same as moving 5 counterclockwise. And that would go to 8 and would go to 3. So because I can get a group of 4. I can then get any by moving with 15. I can then get any multiple of 4. Right? Because then we could also do 16 of them by adding in another one, say 1 to 16 to 11 to 6 and back to 1. Get another square in there. So that's kind of interesting. Now, what sort of shape? So obviously this square works, but well, could we just have one person? So what makes the square special is that it's I think the shape is determined by the k. So maybe instead let's say what are the possible k's? Well, you could have k as 1, so everybody shifts over by 1. But if that's the case, then 1 would go to 20, and 20 would go to 19, and you get sort of a 20 gone. So the minimum number of people I would need to complete sort of a nice enclosed shape would be 20. So n is forced to be 20. That's the smallest n that will work. If k is 2, we can get sort of a decagon, skip every other person. So 1 will go to 19, will go to 17, will go to 15, will go to 13, and so on. Every odd number will be picked. And so the minimum number of people I need is 10, but I can also get any multiple of that. So I can also have 20. Okay, now I don't want to keep doing this for, I mean, I could, do k equals 3, k equals 4, and so on. But I think that would be a waste of my time, and I want to leave time to do B3, B1, B2, and B3. Right? We have to be smart about this. And oftentimes, A6 is harder than B1, and in some cases even B2. So if you think, well, I've got a way to do A6, but my goodness, it's going to take a while. Remember, it's not worth as many marks as B1 and B2, right? So perhaps instead we focus on doing B1, B2. We come back to this. If we find we have a bunch of time, and maybe we just can't do B3, then we could go through this slowly. Okay? I don't want to do that. I also don't want to start a video about B1. So I'm going to try and find a faster way to do this. So with 1, the smallest I got was 20. With 2, the smallest I got was 10. I'm predicting that for 3, the smallest I'm going to get is 20. We can even try it out. So if I used 1, 1 would go to 4, which would go to 7, which would go to 10, which would go to 13, which would go to 16, which would go to 19, but it doesn't close up at 1. It would then go to 2, and then 5, and 8. So why is this happening? Why isn't it closing up nice and neat? It goes to 3, and then 6, and 9, and then 12, 15, 18, and then finally we're back to 1. And I think it has to do with the fact that 3, the GCD of 3 and 20 is 1. So it sort of acts the same as though k were 1 is sort of what I'm trying to say here. I think the GCD of k and 20, if you divide 20 by that, should be the minimum n value for k. So this is borne out by the k equals 1, 3 work that we do. 20 divided by 1 is n equals 20. But when k was 2, well, the GCD of 2 and 20 is 10. Or sorry, the GCD of 2 and 20 is 2. And if you do 20 over 2, you get this 10, as well as any multiples of this. Okay. So I want to test this idea. I could prove this maybe if we had some time. But the idea is, I think, for K, the smallest number of people in a group, sort of like the square or this weird shape or our decagon, must be the GCD of K and 20. Right? No. That's the smallest number of groups. Okay. Basically, the idea is, we go 1 to 4 to 7 and so on. But then when you get to 16 and then 19, yeah, we went to 22, but really, or we went to 2, but really that's 22. And so we're asking, sort of what's the smallest, so if we start with, say, 1, then we keep adding on K and K and K and K so many times. So you get 1 plus however many Ks. When does this get back to 1? What's the smallest number of Ks you need to get back to 1? Well, when these guys are what we call equivalent to 1 mod 20. Basically, when this has the same remainder has the remainder of 1 when you divide it by 20. So then you would need dk to be a multiple of 20. What's the smallest d that gives you a multiple of 20? Well, what factors of 20 are inside k? Well, the biggest factor that k and 20 have in common is the GCD. So d has to be 20 over the GCD. At least that. So that's a more theoretical reason why this would work. Remember, it is a final answer only question. It's A6, so you don't actually have to be explaining this. But, it's my video, and I want to explain the reason why this does work before I move on and actually use it in my calculations. It's also good if you want to leave a little bit of rough work like this in case you screw up the final calculation. You've got part marks sitting there ready to be earned. Okay? So that's the reason as to why it works, is we get back to our original number. If you, instead of calling this 2, consider this to be 22, and then the next one is 25, and so on. So you get back to 1 when you hit some multiple of 20 plus 1 as you're counting up in your arithmetic sequence by k. Okay, so if that's the case, well, then we can make like a nice little chart. So k is, so let's get our k value. Let's get our GCD of k and 20. Our minimum n value, or actually, we can just figure out the n values from there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I will make a little mini copy of this chart over here. 15, 16, 17, 18, 19, 20. All right, the GCD, 1, then 2, then 1, 4, 5. GCD of 20 and 6 is 2, then 1. 1 down here, 4 for 8, 10 for 10. 1, GCD of 20 and 20 is 20. 1, 1, I mean, the primes are always going to have a GCD of 1 there. 14, that would be 2. 12 would be 4. Every fourth one is a multiple of 4. And then the even ones in between there are 2s, and the multiples of 5 are 5, other than 10 and 20. So there we go. Minimum n value, we'd get 20. And then we get 10 and 20. 20, the minimum n value would be 5. You could have 10 or 15 or 20, depending on how many pentagons you added in. So with 5 here, I mean, that's the same as 15 here. And we saw that was 4, but you could also have 8 and 12 and 16 and 20. And as I'm working these out, I'm noticing that the number of numbers over here is the same as the GCD. There are 5 multiples of 4 between 4 and 20. So all we really need to do once we realize that is add these up. So just grab a calculator to keep track of my calculations. 1 plus 2 plus 1 plus 4 plus 5 plus 2 plus 1 plus 4 plus 1 plus 10 plus 1 plus 4 plus 1 plus 2 plus 5 plus 4 plus 1 plus 2 plus 1 plus 20. And I'm getting 72. And that's all I did. I can do a quick spot check. There's 4 and another 4 and another 4 and another 4. And these 3 are another 4. So that's 20 of them so far. 5, 5, and 10 is another 20. So now we're up to 40. 2, 1, 1. So that's a 4. That's a 4. That's another 4. So that'll be 12. So now we're up to 52. And then a final 20 is 72. So I'm really happy with our answer there. We got 72. You could list all these n's out. They didn't ask us for that. They just asked how many pairs n and k work. And that's what we managed to give them. Okay? A nice little question. I think there is a formula for summing up all the GCDs. I don't remember off the top of my head what it is, but I feel like the last few years GCDs have been coming up on Waterloo contests. I feel like there was a Hypatia 4 in, I want to say, 2015, 2016, and a Euclid 9 or 10 the year after that. And this also is heavy GCD stuff. I didn't notice as many GCD things in older papers, but if you're trying Waterloo contest questions around, or you're planning on doing a contest near 2018, like 2019, 2020, I don't know when you're watching this video, you might want to brush up on GCD knowledge and try and spot GCDs in questions. As it stands, that's it for me for Part A on our CIMC. Up next is going to be B1. If you haven't tried Part B, I would encourage you to do so before watching the next video. Thank you guys so much for watching, and have yourself a wonderful day.